So far, we have derived the green strain tensor, and this we can use to describe any large deformation of structures. So even if you have a very flexible structure made of rubber, or you have a very tall building under wind loading which deforms very much because of the wind, you can use it to simulate collapse. You can do whatever you like with it. It's really quite general, but it is quadratic in displacement, which means it is nonlinear. So solving problems with Lagrange with green strain means it is going to be a nonlinear problem and very difficult to solve. So what we want to do is to look at approximations that would allow us to use linear theory, which is much easier to solve. And we do that by assuming small displacements. So we try to derive the small displacement strain. And we do that by starting from the green strain, which says EG is H plus H transpose plus 1/2 H transpose H. And simply we say if H is small, which is the displacement gradient, and this is what small displacement means, then we can neglect the quadratic terms with respect to the linear terms. And we end up with what we call the small strain tensor epsilon, which is really nothing other than the symmetric part of the displacement gradient, H plus H transpose over 2. This is usually written in Cartesian coordinates as follows. I'm going to write down only 1/2 of it since it is symmetric. Gamma xy over 2 and gamma x and over 2 epsilon y gamma yz over 2 and epsilon z, and it is symmetric. The purpose for the 2 will become apparent later. Given the expression for the displacement gradient, it's not difficult to derive that epsilon x, for example, is ux, and for example, gamma xz would be equal to u comma z plus w comma x, and so forth and so on. So we end up with fairly simple expressions for 6 strain components: epsilon x, epsilon y, epsilon z, gamma xy, gamma xz, and gamma yz. And these expressions are linear in displacement and very easy to use, and these expressions will form the basis of what we do for the rest of the course. But just calculating strains is not really the whole story. It would be also nice not to know, because strains actually measure how much the material deformed. If you remember, we said that the deformation in general is composed of 2 parts, a rotation and a stretch, and this is polar decomposition. So it is also good to know if the displacement gradient is small, how the rotation looks like, and this will give us a complete picture of deformations when the displacement gradient is small. So to do that, we start from F equals R times U, where F is the deformation gradient, R is a rotation matrix, and U is a symmetric matrix which measures the stretch in the structure. And since R is a rotation matrix, we know that R transpose R equals a unity matrix. So F itself is I plus H, where H is the displacement gradient. If H is small, then F is nearly unity. If F is unity, this means no deformation, because vectors before and after deformation become the same, identical. So this would mean that R is also unity and U, the stretch, is also unity, no stretch. So what this would mean is that if F is close to unity, then R will be close to unity matrix and U will also be close to unity matrix. So we can write this as I plus a small change, let's call it delta R, times I plus delta U, where these are small changes in R and small changes in U. If we multiply and neglect multiplications, because if delta R is small, delta U is small, then multiplication is so small that we can neglect it, then we can write this as I plus delta R plus delta U. And from this we can write that H, which is our displacement gradient, is approximately equal to delta R plus delta U. So now, instead of thinking about it in multiplication terms, which is the large deformation case, for small displacements, we just say that the displacement gradient, which measures the local deformation, is just the sum of a contribution from rotation and a contribution from stretching. So it is much simpler than multiplication. But how to get delta R and delta U? Because in principle, if we know the displacements, we know H, but we don't know delta R and delta U. In order to uniquely determine delta R and delta U, we take a look at the definition of a rotation matrix. If R transpose R is going to be a unity matrix, then I plus delta R transpose times I plus delta R is going to be a unity matrix. If we multiply through and neglect again higher order terms, delta R transpose delta R, then this will lead us to conclude that delta R plus delta R transpose equals zero matrix. And what this means is that the symmetric part of delta R is equal to 0. And since any matrix can be decomposed into two parts, the symmetric part and an anti-symmetric part or skew-symmetric part, if the symmetric part is 0, this means that delta R is a skew-symmetric matrix, and as such, H equals delta R plus delta U means that delta R is the antisymmetric part of the skew-symmetric part of the displacement gradient, and delta U is the symmetric part of the displacement gradient, which makes sense because then delta U becomes equal to our small strain tensor epsilon, which is what one would expect. So for small deformations, our stretch is just unity matrix plus the small strain tensor. And our rotation matrix is just unity matrix plus the antisymmetric part of our displacement gradient, which is 1/2 of H minus H transpose. Yeah, okay, so now let us look at this matrix here, which we call delta R, and see how it looks like in components, we'll see that delta R will be equal to, of course, all diagonal elements are 0 because the matrix is skew symmetric. This would be u comma y minus v comma x. This will be u comma z minus w comma x. This is again 0. This is going to be v comma z minus w comma y, 0, and skew symmetric. So I don't have to write down the rest of the components. Very well. So what does it mean? If you look at a skew-symmetric matrix, which is 3 by 3, you will see that it has only 3 independent components. Everything else is either just a minus of one of these or a 0. And a vector in 3D has also 3 components. So you can make a correspondence between 3-dimensional skew-symmetric matrices and vectors. They are not vectors themselves, but they correspond to vectors. And if you order these vectors in a certain way, then the vector physically represents the axis of rotation of the rotation I plus delta R. And when you do that, you will find that there will be 3 components of rotation. A component around x, which is going to be 2 times that component, phi, is going to be w comma y minus v comma z. 2 times phi y is going to be uz minus w x, and 2 times phi z is going to be equal to vx minus uy. And this defines the rotation. Just to see how this works, consider a 2-dimensional displacement field, which is given by u equals k times y. So if this is our plane, each point, and v equals 0. So each point will move parallel to the x-axis a certain distance, which is proportional to distance from origin. So if you start with a rectangle of this shape, you will end up with a parallelogram that looks like this. Okay? We used to call this pure shear, and it does include shear for sure. You can easily see that if you calculate your epsilon x, it will be derivative of u with respect to x, which is 0, your epsilon y, which is derivative of v with respect to y, which is 0, gamma xy is u comma y plus v comma x, which is equal to k. So this means that this is a constant shear strain. But it's not only shear strain that's involved. There is, if you calculate the rotations, of course, in 2D, the only possible rotation is rotation around Z. You will see that phi Z will come out to be minus k over 2. So what this means is that if you want to have pure shear with no rotation, we should have had a slightly different displacement field. It should have looked more like this. So halfway this way and halfway the other way here, and then of course in parallel. Yeah, that would have been pure shear and no rotation. But in reality, we both sheared and rotated the specimen. So pure shear would be symmetric in the rotation between x and y. So this line would rotate up the same amount that the y-axis rotates down, and as such, the net rotation, the average rotation is 0. But in this case, in the case we're considering, which is represented by the red line, only the this vertical line here rotated down, yeah, and as such, the average rotation of the two axes, because x remains in the same direction, the average rotation will be equal to k over 2, and it is counterclockwise, and this is why we have the negative sign. So that's pretty much the situation we have. So let us think about it now this way, that the displacement gradient h is composed of two parts: a symmetric part, which represents strain, and an anti-symmetric part, which can be written as either a 3x3 matrix, which is, we call it phi, or we can, corresponding to that 3x3 matrix, write it as a vector, as a 3x1 vector, which would be along the axis of rotation. So the symmetric part of the displacement gradient, strain antisymmetric part, is rotation, and h can be written as epsilon plus p. Okay, now we can go back to our green strain in order to discuss what we call moderate rotations. The thing about strain is that for most structures, strains at yield are in the order of 1%. So, and since we usually don't like our structures to yield, and if it's composite, of course, they don't yield, they are brittle, they break. So we always design in the range of fairly small strains, maybe of the order of 1% or lower. So epsilon is always small, but rotations can be large. Nothing can stop our structure in principle from rotating, because if a structure rotates 10 degrees or 20 degrees, it is not going to break because of that. So having a stiff structure, if it is sufficiently stiff, it will have both small strains and small rotations, in which case H is going to be quite small. And we can indeed assume that our green strain reduces to the small strain approximation epsilon, and we're done. But sometimes the displacements are larger without having significantly larger strains. So we have larger displacements, so H is not very small, but the strains are small. And in that case, what happens is that the increasing magnitude of H can only come from rotation. So let us say that our strains are of the order of 1%, and our rotations are of the order of 0.1 degrees radian, which is maybe 5 to 10 degrees, roughly in this range. So in this way, H is no longer of order 0.01, it is actually order 0.1. So it would look like we cannot really 100% neglect the quadratic terms in Green's strain. And then we have to go fully nonlinear. But we can substitute and see which terms we can neglect and which terms we may not neglect. So if we do that, we'll find that Green's strain is the symmetric part of the displacement gradient, which is epsilon, plus 1/2, which is H transpose H. Epsilon transpose is actually epsilon, and phi transpose is minus phi, because phi is skew-symmetric and epsilon is symmetric. So when we multiply through, we end up with the following: that Green strain is epsilon plus 1/2. We have epsilon transpose epsilon plus, which is like epsilon squared. Then we have epsilon transpose phi, which is like epsilon phi, plus phi transpose epsilon, which is minus phi epsilon, plus phi transpose phi. Yeah, okay. So now let us take orders of magnitude. So this term here is 1%. This term here is 10 to the minus 4. This term here is 10 to the minus 3. This term here is 10 to the minus 3. This term here is 10 to the minus 2, so it is again 0.01. So we will neglect these terms because they are significantly smaller than the linear term, but the phi transpose phi term cannot be neglected anymore because they are the same order of magnitude. And as such, we can approximate our Green strain to be the linear strain plus quadratic term, which depends only on the rotation. And this is going to be the basic equation we use whenever we go for nonlinear theory. So all our buckling predictions and our derivation for buckling equations, stability equations, will be based on this equation here that says that Green strain can be approximated as the small displacement strain, which is linear in displacement, and then quadratic terms, but they are not linear function of the strains, they are function only of the rigid rotation.